In this review, we're going to look at what happens if we have an open in our fuse or one of the phase windings in a Y or delta connected load. So here we have a Y connected load hooked up to a 120/208 three-phase supply. Now, first thing we'd have to do is see how much power this could produce as connected. And of course, for the Y connected load, we have to use the formulas for the Y system. And for 120/208 over here, generally the 120 would be the phase, or we could calculate the phase by going E line divided by √3. And then we can solve for the current down each branch. And of course, for our total power, E line times I line times √3 gives us the watts. Now in this case, power factor is important, but because it's a totally resistive load, power factor is 1, and we can ignore it. Now if this was an inductive load, you would have to know the power factor or the angle to figure it out. We could also go E phase times I phase times 3. We have 3 phases, so that makes sense. And we get the same power either way. Now what would happen if we lost, in this case, C fuse? How much power would this circuit produce? Without a neutral, if we lose C phase, all we have is basically a single phase circuit with 2 resistors in series with each other. And because they're in series, each of these will drop half the voltage. They are connected across 208, which is a line-to-line voltage. We can figure out the current for the circuit as if it was a single-phase circuit. Now we could use 208 divided by 24 or 104 divided by 12. Either one would give us the amperage for the line of 8.67. And now we just simply go E line times I line to get our power. In this case, 1800 watts. Now we could go 104 times 8.67 times 2. That would work as well. Or we could also go E squared over R would give us power. Now we'll notice from the previous circuit that we produced 3600 watts, and now we are only producing 1800 watts, which is 50% power. This would be true if we lost a phase winding as well. Now we'll look at the same circuit, but in this case we do have a neutral. The Y connection rules apply. I line equals I phase. E line equals E phase times √3. And of course, even with the neutral, our power is the same. It's a balanced 3-phase circuit, so it makes sense that it would be the same. So 3600 watts with the neutral and without the neutral. Same scenario, we've lost C phase fuse, but we have the neutral now, and each of these windings will still see 120. We'll see 0 volts here because we've lost our fuse, so no current, no voltage drop. We can calculate the amperage. And of course, in this case, we have 2 of the phases that are still working. Third one's done. 120 times 10 times 2 gives us 2400 watts. Before, these each dropped 104, but because of the neutral, these each are going to drop 120. So with the fuse intact, we drop 3600 watts, or produce, I should say, 3600 watts. With a blown fuse, and we have a neutral, we produce 24, which is 66.66 power, or 66.67. And that would also be true if we lost a phase winding. Now we'll look at a delta connected load. In this case, we have 240 volts, 3-phase, connected to a delta load with 24 ohms each phase. How much power can we produce? Well, we have to use the rules for delta, E line equals E phase. And we can calculate our total current for each phase. But remember, for delta, I line equals I phase times root 3, which gives us our line current of 17.32. For total power, we can go E line times I line times root 3. And once again, power factor is purely resistive, so it's 1. And we can see that we produce 7,200 watts. We can also use our phase values, just like with the Y connection. In this case, 240 times 10, which would give us 2,400. Of course, times that by 3 to get 7,200 watts. How much power would it produce if we lost a fuse? This is actually called single phasing, and so basically we have two resistors now in series with each other, but in parallel with the other across 240 volts. 240 will be the same here as normal. But now because these are in series, if you track the current this way, nothing's going to go this way because of the open. You can see that each of these are going to drop 120 volts now, which in turn would be 5 amp down this branch versus 10 down the other. Now we could have went 240 divided by 48 to get the same results. Either one would work. And here we have the power, 240 times 10, also 240 times 5, 1200. Add them up to get 3,600 watts. So when the fuse was intact, we produced 7,200, and with a blown fuse, we produce half, or 50% power. This is the same circuit being drawn as a single-phase circuit. Hopefully that makes a little more sense. We could have did 120 times 5 and got 600. So I'm showing you here that you could do it that way as well. There's always a couple ways of doing things. We could have went E squared over R as well to get power. It doesn't matter how you get there, as long as you follow the same method each time, you should get the results. Now let's look at it with an open load or an open phase winding. Same circuit as before, but now instead of a fuse, we've lost a winding. In this case, E. You calculate the total power produced by each load. You could go E squared over R once again to get P. Here, we've got no amp, no circuit. We have a potential, 240 volts across there, but no current draw, so no power produced. Here, 240 divided by 24 gives us 10 amps. We can figure out the power, 2,400 each. To give us a total power of the circuit of 4,800. So before, with the phase winding intact, we produced 7,200 watts. Now with it open, we only produce 4,800 watts, which is 66.66% of the power. So in summary or review, a Y-connected without neutral produces 50% power when an open occurs in a fuse or phase winding. If it has a neutral, it produces 66.67% power, whether we have an open in the fuse or the phase winding. In a delta connection, open fuse produces 50% power, but if we have an open in the winding, we produce 66.67% power. Makes sense.